Let's sit down so we're comfortable. So let's play with impulse and momentum. So do you have a sense? I'm not the kind of person to ask these kind of questions, but I probably should be. If I asked on a test, like explain impulse, like, or, do you have people ask you what you did today and you're always like, I don't know if I should tell them because they're not going to want to hear this. But did we chat enough about impulse and momentum that you have a sense of a feel for what those are, even though you're going to kind of forget that, based on pushing kids on the swing set, that idea, just the concept that if momentum is if something is in motion, there's a quality to that motion, which is based on its weight and its speed, mass and velocity. But then stuff can happen to it. It can get knocked in some way, which is going to, of course, change that. And so let's play with this with respect to a baseball example. And this is kind of a cool problem because it actually, it's in a sense like a final exam almost. It sort of brings up a lot of the things we've talked about since we started this class, which is kind of why I want it to be low key. I don't want you to have to do an assignment. I just want you to, I don't know, think about this with me, enjoy, ask questions, wonder. But let's say this. Let's say you want to hit a home run, HR, and straight line. And so we'll say there's this fence out here like there is in the pros, and you smack a home run over that. Kind of goes like this. We'll say it's a 300-foot fence away. We'll say it's a 12-foot tall fence, and we'll say you strike the ball 3 feet off the ground. That all sounds about right, doesn't it? Can you appreciate the fact that there's a lot of ways to get there? What I mean by that is this. Could you also not hit your home run, maybe less on a line drive? Something more like that. Of course, it's, willing to go way over the fence. I'm just calculating it as like right at the fence. So, okay, that's kind of cool. We've studied projectile motion. So when you see that, you should kind of feel like, I know some things about that. And, I understand I can hit the ball with a certain amount of force, but I can also hit the ball with a certain amount of velocity. And but velocity, and this is kind of the reason I'm bringing this up now, velocity is a little more nebulous. It's not like you could stand there with your bat and go, okay, I'm going to go for 112 and hit it. You can only really just hit it with a certain amount of force. And actually, that probably could be measured. And that'd be all you got. Like you can't do any more. You can't choose. I mean, you can choose to hit it with less, just kind of tap at it, but you can't necessarily do it with more. So if you think of full power, I hit it with full power, whatever force I have. That's going to maybe cause a velocity, and I have some control over the angle, although with the ball coming in super fast, most of that is the ball being a little bit on the high side of your bat will make it go up, a little on the low side of your bat will make it go down, and you just sort of get what you get because it's too hard to kind of control that. And that's kind of why I'm bringing it up now, because I really only have a control over force. But remember when we did all those equations of motion, parabolic motion like this, they didn't have force in them. So, how would that work? Like, what kind of a force would it take to bring this about? Am I capable of hitting a home run? So really, I just want to kind of play around with that a little bit, sort of see what that might look like and what mass and velocity and the stuff we've been studying would have to say about that. I'll zoom in over here and just kind of throw this in. So in other words, if this is the horizontal, then I can hit it at different angles. And so I'm putting theta in there as an example of that. And then of course I can hit it at different velocities too. And I don't know if you actually know this, but if those two balls kind of landed in the same spot right at the fence, do you know that those two velocities would actually be different? They have to be different. Do you know what's harder? Like what would have to be a larger velocity? In other words, you hit it harder. Which one of those two, the green or the black home run? Why do you say that?
Because at that point, you're also fighting against gravity more, and it's a longer distance.
You're sending it uphill, and I'm not commenting on whether you're right or wrong here, but you're sending it uphill, it's flying further, you're fighting gravity more because it's going up in the air. So your sense is I got to hit it harder to get it to follow the green line. What's that?
It's gonna have a bigger slope.
Absolutely going to take off with a bigger slope.
Is it, which one is gonna have more velocity?
Yeah. Did anybody think
I
so?
would say the black one.
I love it. Disagreement. That's what I was hoping for. Why do you say the black one? Caesar thought the green got to go higher and fight gravity more, so they'd have to hit it harder to follow green. You say no, it's black.
It takes less time. And from experience, it's harder to hit a home run and a line drive.
Yeah, so you're saying it kind of from experience. Well, think about this simple example. If I just have this little pin cap and I'm like, I'm gonna throw it. If I'm gonna throw it straight at you, like I won't do it. I'm gonna throw it like kind of like try to hit you in the nose, so to speak. You guys all think about this with respect to experience and feel. If I want to hit him in the nose, I'm kind of throwing it basically at his nose. I can't, if I throw straight at his nose, it'll never hit him, right? Because it's going to drop between here and there. It's like no matter how hard I throw, it's going to go below that a little bit. Let's say I aimed at the bill of his hat, just a hair above his hat, and I'm going to hit him in the nose. Do I have to throw that hard or easy? I got to throw it pretty darn hard because it's going to fall as it flies through the air. So actually the right answer to this question is indeed the black one. We'll play with that a little bit later, but the more that it's on a line drive, the harder you actually got to hit it. Now, interestingly, there's a happy medium. Like if you want to hit it as light as possible, there's actually, so you're actually not wrong either, Caesar. If I make that really tall, then you got to hit it really hard with a ton of velocity. And so there's actually a minimum there, which is sort of a calculus problem. What's the minimum velocity you could hit it at, hit a home run, and it'd be a certain angle. And because I made a Desmos, we're going to play with this a little bit later.
Slope is velocity. How come?
Well, slope is velocity when you think of it as feet per second, feet on top, seconds on the bottom. That's a slope, or a rise over a run. But velocity is not the same as that angle. Those are related, but it's not exactly the same. Let's take a look at this. I've got a Desmos app on my giant phone here. My big phone. I think this will work on here. So I want you to stare at that velocity. So I got rid of all the equations so it wouldn't distract you. And I have angle of departure A. And so it's 50 degrees right now. Does that look like 50 to you? And you can't see, but can you tell it's leaving at 3 feet? Like I designed it so it would leave at 0, 3, and then it flies out there to the point 312. X is 300, Y is 12. And so notice that's 100. In this case, because the measurements are in feet and seconds, that's 100 feet per second that it would take to get it to that location. But let me see, can I just touch drag this? Apparently I can. Notice what I said before, or the part of what Tristan said that's true. Do you see how hard you got to hit that thing? Now you don't know where that equation came from yet that that allowed me to build velocity. Like where did the velocity come from? Like, but we're going to build it in just a second. Notice if you want to hit it that flat, you got to hammer it, man. It was 100 a minute ago. Now it's 174, feet per second. You got to hammer that thing.
So then when you would basically have a straight line up to its maximum velocity.
Yeah, interestingly, it goes to, if I keep going, watch what happens when it gets to a straight line. See how it's just getting crazy now? 394, 991. How come it just went away?
You're not going to make it. It's going to hit the ball.
Exactly. If you wanted to hit it straight to it, it has to be infinite, which again, maybe because you've taken calculus, you're a little more comfortable with infinity than you would have been prior to that, because it's not really possible to hit it in infinity. And yet in calculus, we said, okay, let's hit it infinitely hard. And then it actually went in a straight line. So that's kind of interesting. Look at it when you go the other way. I don't know if I made this big enough, but notice, do you see how it got to a minimum there of 99, 99.8, 99.9? Do you see how it's sort of going up again?
So to maximize your velocity, would you want to set it to a 45-degree angle?
Yeah, that's interesting. Well, to minimize your velocity, you mean?
I mean,
If you want to maximize your velocity, you need to hit straight at it, because that'd be an infinite velocity.
I guess, but I mean, for that given 106 meters per second, if I hit it at a 45-degree angle, that's the furthest the ball will travel.
Yeah, so no, because this is designed to hit the top of the fence. Basically, the velocity and angle work together to get it to hit the top of the fence. If you hit it at 60 degrees and you hit it harder than 106, then it'd just fly out of the stadium. So every one of mine is bouncing off the top of the fence. You see what I'm saying? So did you notice it's getting larger? Now I had it stop at 60 degrees, but you can probably appreciate, actually, I think I can probably change this.
90.
I'll
Right,
put-
taking the-
I typed it.
I'm going to find the 90, but what about 89?
Okay, so I just increased the range now. Watch what happens to speed now.
Does that mean you have two max velocities?
Yeah, so if you want to hit it sort of, if you hit it straight up, it'll come back and hit you on the head. So you can't actually hit it at 90. Does that make sense? But you can hit it at 89.99999. And you can see it's going off to infinity again. So interestingly, which is again, just a playful concept, but if I just kind of grab this, what is the minimum? And this is kind of what Thomas was getting at, except for at least I think I'm understanding his question. I'm trying to find the minimum one. So notice that's 99.7977. It's like right there. Notice it's not 45 degrees. Isn't that interesting? So if you want to hit it like, you want to hit a home run, but I don't have energy to hit it at 600 feet per second. So I want to hit it as easy as possible. It's like, it's not even 45. And actually it would be 45 if it left it 3 feet and landed at 3 feet. If the fence out there was 3 feet tall, then it would be 45. But the fact that it's got to go a little bit higher. So that's just kind of interesting. So, you can at least imagine, you wouldn't necessarily want to have to do this, but you could imagine somebody could create a calculus problem and say, what's the minimum speed it could be hit at? What angle is that at? And so forth. Again, that's probably overdoing it in this regard, but I think of something in a sense more fun is kind of like, okay, I've got like that pool that those guys slid down the ramp and flew off into the pool in that water slide. It's like I'm going to shoot my gun and I'm going to aim, up in the air. I'm talking deer rifle, so it's going to go, tons of miles or whatever. The idea that you could there's a hill like 4 miles away and you're aiming way up in the air, and it lands like where you want it to land. The idea that you could just, I don't know, make some progress with that in this class, even if it was just for the fun of it,
Like if a pitcher threw it at 100 miles an hour, like at that velocity, would you have to actually sweep? Just like,
That's a super interesting question, isn't it? Because that's part of something we're going to talk about in the next chapter on Tuesday, which is something called the coefficient of restitution. In other words, when the ball comes in at 100 miles an hour, the bat's going to absorb some of that energy, kind of frictionally absorb it, so it's not going to leave at the same speed, but you'll get some percentage of it back. Now, if you've ever played baseball, when you bunt, you actually try to pull the bat back a little bit because you don't want it to roll straight to the fielder and then they'll throw you out. Like you want it to die. And if they throw a normal pitch, it'll hit the bat and bounce too far out and you'll be out. So you gotta kind of receive it a little bit, gotta have some touch, and you also gotta send it not to the pitcher because he's really close. You gotta send it down the line, ideally third base because it's for the throw and all that. But yeah, that's exactly right. I mean, if somebody threw hard enough and you were able to kind of stand there, you can appreciate your muscles are going to give even if you try not to. But if you had a hard enough bat, you had a hard enough ball, like more like a golf ball. Golf balls are, made of, you ever tore a golf ball apart? There's rubber bands. That's all that's in there. It's kind of cool. But if it's springy and if the bat is springy, then theoretically, if somebody threw hard enough, yeah, you could bunt a home run. Totally true. Just don't get hit by the pitch. So let's see, perhaps we'll come back to that, but let's start playing a little bit now with this idea. So we've decided we basically, and I'll go ahead and write this in here just to make sure if we need it, it's there for us. But that's the 0.03 and this is the 0.312. And so that's all we really know about our parabola. We know it's flying through the air roughly in the shape of a parabola. I say roughly because there is wind resistance and that screws up the parabola. And that's it. And so that's not enough points to define a parabola because again, we have so many options as to how to hit it. But let's just play with this for a second based on equations that we already know. Again, this is only for fun. I'd rather you just reason with me, think about this. So here's our basic I just chose to write it backwards, kind of in ascending order instead of descending order. And of course, same thing is true for y, right? I just replace all the y's, all the x's with y's. So that was our early equations that helped us kind of understand this type of motion. So it's like, well, what do we know? Again, we know some things here. So what do we actually know when this thing, if this is a home run? I mean, those are generic for any kind of motion like this, but let's just think about this a second. Don't we know that the initial x, if I consider this to be the origin, the initial x is actually nothing, whereas the final x is out there at 300. True? Know that. Let's see, what else do I know? Do I need know anything else about that equation? No, the beauty of this problem is we're going to try to hit a home run and we're going to try to figure out what that velocity would be. Now, we did do that before. We tried to jump a bike and get it to land in a certain spot.
Is
So
this after he hits it or before he hits it? Or at?
this is really just the path of motion. So this is,
Acceleration is 0.
good job. This is a home run. In other words, that's why I was able to put 300 in there. Does that make sense? It started at x is 0, it ended at x is 300. So it's still the green or the black path. We haven't chosen a path. But yeah, there is nothing getting it to accelerate in x, at least if we simplify this and say frictional wind resistance is negligible. And so notice we have a fairly simple equation. What is that? 300 equals V0. And I'm going to change V0x just to V and then modify it with the cosine of theta. And I'm only doing that because I don't want a V of 0x and a V of 0y. You may remember that from before.
Times time.
And times time, which I left out once before. But so would you agree that's kind of like our equation that models the horizontal motion? But notice it's not very satisfying because it has V's and thetas and T's in it. Of course, we could pick a theta. We could say, okay, let's hit a home run, at this angle. And actually, we're going to do that in a little bit. What about that second equation? What do we know about that?
You know the y, starting and final.
Yep, we know the initial y because it was 3 feet off the ground when it hit. And we know the final y because it was 12 feet high at the fence. What else do we know?
Acceleration is net gravity, but would it be negative?
That's right. That would be negative. So, which I always forget. So thank you. Yeah. So because we're doing everything in feet, then that would be that. And I multiply by 1/2 and it becomes 16.1. So let's see, if I subtract 3 over to the other side, that'd be 9. So I guess this would be 9 equals.
So you do the V sine of theta.
Yeah, and instead of V0y, I'm going to say V sine of theta. So now those two equations can speak to each other. And I guess that'd be minus 16.1 t squared, right? So in a sense, it's just like the top equation in the sense that it has V's and thetas and T's in it. And so now I, if you will, I own the path, or at least I own the relationship between velocity, theta, and time for any path I would want. And so now I could pick a path just to make, make life a little bit simpler. But first of all, let's just see what we can do with this a little bit. Does it make sense that this top equation up here, if I solved it for t by dividing v cosine theta away, then I could actually come down here and replace that, the two t's down here, by combining those equations. Notice this isn't two equations, two unknowns. It's two equations, three unknowns. So I'm not going to solve this and get an answer, which makes sense because there's lots of different paths. And so I'm not going to get one answer for every single path, because we just saw a second ago, every angle had a different velocity. But I can get rid of t. I mean, isn't that kind of cool? I can take the time out of this if I choose to not care about that. Of course, I could take any of these letters out of it. But if I did put that in there, let's see what I would get. So I'd have 9 equals velocity times the sine of theta, and then times t, which we now just figured out is 300 over v cosine of theta. And we have our negative 16t squared, 16.1 t squared. But again, we just figured out t was 300 over v cosine of theta. Can't forget to square that. Algebraically, what happens that's kind of nifty with that first expression?
It turns into tangent.
Yeah, notice you have velocities canceling. You have a velocity on top and the bottom, and then you have sine over cosine, which you could certainly leave alone, but you could also write it as tangent. So actually we have 9 equals 300 times the tangent of theta, which cleans that up a little bit. And then the other one we can't really clean up. I could square 300 and multiply it by 16.1, I suppose, but I guess I won't, just because I don't want to figure it out. Now, that's kind of cool. So basically what this says is, hey, I've got an equation with 2 unknowns in it. I'm still not super happy with that because it's got a v and a theta. But of course it has 2 unknowns, because any given theta now, does it make sense I could solve for v? Well, that's what I just did in Desmos a minute ago. I picked a theta of 50 or whatever, and then just spit out the velocity. So I've got this velocity equation now. I won't take the time to do this. But if I did solve this for v, I won't take the time to like algebraically show you, well, I can't live with that. That was like a drunken square root sign. Still drunken. What's going on? 16.1 times 300 squared. Again, I could certainly figure out what that is. And then you get cosine squared of theta times 300 tangent of theta minus 9. So this is why we study algebra. Thinking back a little bit, you've suffered through lots of algebra classes, but do you understand how much more useful that equation is than the previous one? The previous one wasn't solved for anything, whereas this is now designed that you can pick any theta you want and it'll spit out velocity. Of course, I could do it the other way too, right? I could put a velocity in there and it would spit out the theta too. That'd be kind of cool, maybe to have that too. So this is what I had programmed into Desmos earlier, then that's why it was doing what it was doing. So that's kind of interesting. Now, all told, that's not new to you. We played with that equation before, and so now I can sort of, hit at a certain angle, and I know what velocity I need. But the problem is although I could pick an angle theoretically, I mean, it's kind of hard, as I said before, to hit and be at a certain angle. I can't really decide to hit a ball with a certain velocity. I could decide to hit it with a certain amount of pounds, even then, I don't know if I can control it, but I have some control over it. I'd have a maximum I could hit it at, and then I could take that all the way back to 0 theoretically. So that's kind of cool. But what I really want to do is kind of think about, I want to hit a home run. Awesome. That's my goal here. And this tells me angle and velocity relationship, but as I said, this is not really what I want. I want something that I can control. This is not like the mountain bike. In the mountain bike, you can actually control your velocity. Oh man, it was a great wreck last night. I gotta tell you that too. I do something fun after school every day. I got this friend who's gained like 50 pounds and he decided, all right, I'm gonna get a mountain bike, go mountain biking. And so we biked on this trail behind my house, and he's not that good at it yet. And we were just, curving around. It's a full downhill trail. We're curving around, and there's this one super steep left-hand corner that is banked and it goes downhill, and it's kind of frightening and so forth. And it's kind of hard. And I thought, I wonder if I should yell at him about this corner. And I thought, oh, well, he'll figure it out. And so I'd go down the corner, and not only that, somebody had put like a jump in it. And there was like a ditch, kind of a ditch, and you had to jump it. And I've been on it enough that I had enough speed, I was able to like, oh crap, and jump it, and everything was fine. So I stopped and I thought, okay, here we go. I turn around and he's going around that corner really slow, and he gets to that ditch and his front tire goes down in the ditch. And at that point and I'm telling you this partially because it's funny and partially because of, well, torque. Basically his center of mass got beyond the front axle of his bike, because his tire goes down inside it, and then he's like, oh, and he flew, and the hill kept going down. So in a sense, he kind of fell through the air 10 feet and let out a big old like, oh, like you do when somebody punches you in the stomach. I wish I had a video of that. It's so awesome. He didn't get hurt though, so I wouldn't be laughing as much if he got hurt. But it's like dynamics, man. That was a pretty dynamic crash you had there, bro. Okay, so let's get some other info involved here. Let's pick a few things. So I'm just going to make up a bunch of stuff. I can't remember how realistic this was, because yesterday I showed you kind of a baseball. Let's say you contact the ball for 0.015 seconds. I think yesterday it was way smaller than that, a lot less seconds. Let's say the pitch is 90 miles per hour, because that's not the right units. I won't take the time to do that with you, but that's 132 feet per second. Hopefully you could easily make that conversion yourself if I gave you a little bit of time. And let's just say, I don't know, he hit it at 50 degrees. And again, the only reason I'm doing this is I'm not just bringing this up to bring it up, is because I'm thinking the equations that we just studied. The equations that we just studied, we said that mass times initial velocity plus impulse. So momentum plus impulse, in this case, there'll only be one impulse, will equal the mass times the final velocity. And I'm thinking, hey, that gets force involved. This is how velocity turns into force. And again, part of my job in this class, because I don't feel like it was done very well for me personally, is to help you learn how to think more deeply algebraically. So before I was sort of stuck in velocity theta land, but I was thinking, well, I don't have control over those things. I'd really like to know force. Hey, here's an equation with velocity and force. Maybe I could throw a velocity in this and it would spit out a force, and maybe I could control that. Of course, it'd be kind of fun to, hit a home run, if you will, with a machine. Like you could actually control that in some way and kind of see if it actually worked, and maybe study the wind resistance part of it when it actually came up short, right? Because there really is wind resistance. So the idea is, could this actually help me make this path happen? Because that's really my question. I mean, I can draw the picture of that path, and that's really cool. And not many people can do that, except for guys like you now. But how do I actually make that happen? How do I make the ball follow that path? As I said, the only thing I really have control over is force. And so let's kind of play around with that for a few minutes. So first of all, let's say this, since this equation up here is really kind of like velocity is a function of theta. Notice what that means algebraically is on the other side. That's the only letter you need to know, and then you'll be able to spit out velocity. And so down here, if I say, okay, well, let's do that. And again, in the interest of time, I'll just plug that in and let you know. But if you plug in, I'm sorry, 50, not theta. If you plug in 50 degrees into that top equation, you get out a velocity of 100.31 feet per second. So I do know how hard I have to hit it for it to follow that path. That's cool. And so I'm thinking, oh, let's plug that into this. And let's think about the impulse of the bat and try to see if we can figure out the force. Now I'm going to let you in on a little bit of my own conundrums here, but I'm still struggling with this part a little bit. It seems at this point I'm 90% sure that we actually have to consider this problem kind of separately, horizontal and vertical. What I mean by that is, can I throw that velocity in there as 100.31? Does this equation care about the direction of things? Remember the energy stuff didn't care? Didn't matter what direction that velocity was going, it didn't care. In this case, I tried it caring with a horizontal and vertical, and I got one answer. And then I tried it without caring, got a different answer. So now I'm kind of going,
Or if your final velocity, you just plug in well, what would be final velocity?
So, I mean, let's just start playing with this. And again, I'm doing this just to improve your and my conceptual understanding of this. But I'm only 95% sure I'm happy with this, is what I'm getting at. So if you hit it at 100.31 feet per second at a 50-degree angle, then the ball is going to bounce off the top of the fence. Does that make sense? That's what we've figured out here so far. So I have a path, and awesome, it's going to work. Okay, great. So if that's the case, then my ball has an initial momentum, MV, has an initial momentum, doesn't it? So I said earlier, no, we gotta choose a different color. Let's go purple. Purple never gets any play. We said our ball weighed 0.32. I won't rewrite the units because they're up above, but 0.32 pounds. We said it had an initial velocity of 100.31. Now here's the struggle for me. Do I put 100.31 there, or do I have to modify that by the cosine? Well, in this case, because I'm saying it's horizontal, then I've got to modify it. But I was just kind of thinking, do I even need, as I said before, do I need horizontal and vertical? Can I just dispense with that and just leave it out? So at this point, I'm thinking 95% sure I've got to do it separately. And so that 100 was at a 50-degree angle, so I've got to modify it by multiplying it by the cosine of 50, right?
Why do you do that? Portion. And then the velocity is aimed at it.
Actually, let me back up. Let's do this. Let's do this a little bit differently.
Yeah.
Let's do this a little more deeply, like what we did yesterday. In other words, let's think of this as the ball. Like the ball comes in at a certain speed because of the pitcher, and then I'm going to put a force and a time with the bat and hit it. And after I hit it, then it will actually have the velocity that I was talking about. Does that make sense? So we could do it either way, but I mean, let's look at it this way. And of course, mass is annoying here, and I just screwed that up a second ago, but that's not a mass right there. That's a force. You understand that? 0.32 pounds. So I actually have to divide that by gravity to get that to be a mass. We said the other day, I think you guys looked it up, it was slugs. So in a sense, what we're saying here is this is like just after contact now, because remember that final velocity of 100.31 is going to change as it's flying through the air, right? So that's more like the velocity it left at. So just after contact is an important addition there. It's not like it's going to fly at that speed the whole rest of the time. It's going to speed up and slow down based on gravity tugging on it, right?
So the initial velocity is the pitch.
So that's exactly right. So we're thinking of this as like the ball. The ball comes in.
And force and time is the fatter it gave.
Exactly. So this is still the same because we're just talking about the ball flying through the air. And the pitch comes in at 132 feet per second. And I'll simplify this a little bit. Does it make sense that the pitcher's on the mound and their arms up in the air? It's going to be downhill actually a little bit, so that we'd actually have to make a conversion. To simplify this, we'll just kind of say the pitch comes in flat. Think of it as a pitching machine if you want to, only because I just want to keep our focus on playing around with what we've been studying instead of getting too lost in the weeds on this. So pitching machine, it was set up 3 feet high and it's coming straight in at you. You know, not perfectly realistic, but so I'm just going to write the word flat here. It's like a flat. This pitch was flat. Now, per yesterday when I introduced this, like, you know, the ball was coming one way and then it got impacted or impulsed and then went the other way, right? So we got some negative issues. Where does the negative go here? Like, is that a negative 132 and then a positive 100.31, or is it the other way around? Yeah, actually doesn't matter, but I got to pick one. I got to kind of choose a frame of reference. So if I think of the ball coming this way kind of first, and I think of that as negative. So I'll think, okay, the pitch comes in and it's negative. And then I hit it and it goes out positive. If that's the case, then I would choose something over here to be negative. Does that make sense? So, okay, I'll pick that one. And so because this is horizontal, does it make sense this addition is necessary? In other words, this is not just a force, it's a force in the X direction, because when you hit the ball, is it all going to be flat? No, is it 50 degrees? So some of the force has to be horizontal and some has to be vertical. And lastly, we said, and we made this up, that the time was 0.015 seconds earlier, did we not? I'm going to rewrite that S over there because it looks too much like a 5. So we got everything involved here. We got the weight of the ball, we got how much time it hits the bat and so forth. Does it make sense we like that equation? This is what I showed you at the start of class yesterday. We like that because it's only got one unknown. So I can find the force of X now. That's kind of cool. So if I punch buttons on that, naturally I get a positive force of X because you're having to undo the negative momentum of the ball and you're trying to send it the other way. So to get it to turn around and go the other direction, I'm going to have to smack it in the other direction. Again, I'll save us a little bit of time and just punch numbers ahead of time. I get about 130.17 feet per second. Oops, that's not feet per second, that's a speed. What would that be? What would the units of that be? Yeah, and I didn't bring this up again, but remember the ball had a velocity, I'll erase this, but the ball, let's see, 0.32 was pounds, right? So it was pounds over 32.2 was feet per, 32 was feet per second, right? And then we multiplied by a velocity, which was in feet per second. And so this foot canceled with that foot. This might confuse you, but the,
That's the impulse,
let's see.
the amount of force applied over a period of time.
Yeah. So 32.2 is feet per second, right? I'm not wrong about that. That's gravity, right? So the weight was in pounds. Weight, whatever, pounds. So velocity is feet per second. This is a little confusing because it's fraction over fraction. But since those dividing by s squared, the s squared would end up on top. Do you understand that? Maybe I'll rewrite that.
When S gets eliminated, the bottom S gets eliminated.
So you'd end up with seconds squared times pounds on the top and feet on the bottom, and that's multiplied by feet per second. So the feet cancel, one of the seconds cancel. So I guess my units are
Time second.
pound seconds. Is that what it is? Pound seconds. What's that? And that's the momentum. What's the impulse? Force times time. Well, force is pounds times seconds. Pound seconds. Like that was our units. And that's why we said these are actually the same thing. Oddly. Momentum.
So if our force of X is pounds seconds, when it multiplies by time, it gets.
No,
pounds.
the time is seconds. Force is pounds and time is seconds. So it's easier to see here. You have pounds here times seconds there. It's
Yeah,
pound
oh,
seconds.
okay. I thought that whole thing was just for the force of X.
This whole thing was actually for this momentum over here. I was just trying to figure out what are the units of that. So again, it's kind of interesting, but our units here are pound seconds. And so again, it's a force. We said in the previous section with energy, it was like force and distance. This section, it's force and time. So again, just all of that to make you consider, make you think about this a little bit deeper. So all that to say, yeah, in order for those two units to be identical, F would have to be in pounds. And, you know, we knew force was in pounds here, so wouldn't necessarily have to do all of that to pull that off. Now, what I think is cool about this is, does it make sense you could actually potentially do that now? Like I was trying to get the ball to follow that path and I just came up with something actionable. I could actually hit it with that amount of force. I mean, if I had to measure that somehow, but again, as I said, it would be kind of fun to hit it with some kind of machine where we could actually control that amount of force a little more easily than, you know, measuring our muscles, if you will. Okay, well, let's see if we can do that for vertical. What happens vertically? I want to give you a second to think about this though, before I just kind of instantly do it. So think vertical. What's the same? What's different? If the pitch, say that again. Was that Ian that said that?
Velocity zero,
Why do you say that? You're right.
because
We're assuming that it was
so.
If the pitch is coming in flat,
Yeah.
then it doesn't have a vertical velocity. So again, we can complicate this by, you know, having the pitch come downhill and it would have a little bit of velocity and then maybe that'd be more interesting. But so yeah, actually in this case, because it's flat, there's actually no velocity in the y direction.
Why was our acceleration 32.2 in the horizontal? When we divided, when we found our mass.
It's not, there's no, that acceleration is just changing 0.32 to a mass. Like the only reason it's called 0.32 pounds is because you live on Earth where the gravity is that. No, that's an excellent question. Don't shake your head like somehow that was a bad question. That's an excellent question.
Then
I don't think that's obvious at all. So in a sense, notice I just went back and did this. I probably should have called that first velocity in X, and I should call this velocity in Y, right? I should have distinguished that because we did decide we're going to do that. It was under vertical. So it has no vertical speed, again, because the pitch was flat. And so it actually has no momentum in the Y direction. It's not moving in the Y direction. But it has the rest of this. The contact time was still 0.015 seconds. We don't know the force in Y yet. Nothing else on the other side has changed.
The final velocity is gonna be a sine instead of cosine.
Nice job, except for the angle. So that's exactly right. So the mass hasn't changed. Final velocity is still 100.31, but we do have to modify that with the sine of 30. So there is actually a difference. And so again, I like this equation because hey, it's only got one unknown, force of Y. And so that's kind of rad.
Isn't it sine of 50?
50, thank you. Not sure where I got 30. There's been no 30s in this problem. I didn't even crash. It wasn't even my crash. My brain is working fine. That was from 2 days ago, that shiner when I hit the rock. That's what it was. Don't hang out with me in your free time. That's the lesson here, in case you didn't get it. So that's kind of cool. Of course, it would have some positive force in Y because you hit it up, right? So that's kind of interesting. So off the record, just some things that are bothering me. So basically, you hit it this hard and this hard, right? I was sure thinking that would be 50 degrees right there. It's not, it's like 20 or something. That's bothering me. It's not even close to 50. It's like way less. If you do inverse tangent of that. So the fact that I hit it with those two forces, this is I rounded it, but this is my horizontal force. This is my vertical force. It just seems like if I hit it, like, wouldn't that make this, shouldn't that make the same angle the velocities did? And it's not even close.
Well, no, because it makes sense.
Good.
Because you're
Explain it. 'Cause I don't get
because
it.
you have one that's coming in, which is no degrees. And then to subside that, to make it go up to 50 degrees, your force is at, what was it, 20 something degrees, 25 degrees? And the outcome of that is 50 degrees. There has to be an equation that adds both of those incoming angles together to equal that 50.
the pitch is
So
coming in
50 is
flat.
the sum of what those previous actions are.
Explain those previous actions again. I like your idea, but I'm not seeing
The
it yet.
pitch coming in.
Yeah, but we said it was flat.
Yes, so the force that we use to hit it has to. Is our velocity? Yeah, to counteract, to move that ball to go into that angle. I'm thinking as the ball's coming in, the force, the direction of the force that you're swinging, not necessarily the direction of the bat that's swung.
Mhm.
Just those both hitting make up that 50-degree angle of when it leaves off the bat.
This is the forces of us hitting. So.
Yeah, that one is, which gives us
that
a
it's- you're not gonna hit it flat.
You're not, you're hitting a 25-degree angle.
Then how do you get to 50?
That's what I'm thinking, that's the result of you hitting the ball, that's the outcome, you get the 50-degree angle. Because the force is before you hit it. Or it's like right at the hit, not after. Not the ball going off.
And then we apply the impulse, and that's gonna bump it up.
Well, the impulse is at that 25-degree angle. The two actions hitting each other and the result is the 50-degree angle.
We have to add that 25 degrees in order to get it to the.
Well, if it's let's say it's going to the opposite direction, then the ball technically has 180-degree angle. And your swing, your force has a 25-degree angle going the opposite direction. And the outcome of that is 50 degrees. If you do that triangle, do the inverse tangent and solve for theta as a inverse tangent of 1/130. And the other one is 180 and
Well, maybe that's just the additional, so if we do like, what was it,
well, it just
50?
gives us the angle, which is the theta, which is 25 or 20.
Well, so then if we are told that it's going to leave at 50 degrees, does that mean we have a deflection of 28 degrees, an additional 28 degrees?
Felt before the ball leaves.
It's weird how hard this is, isn't it? Because I'll come up with these kinds of questions, having taken physics once as a freshman in college 30 years ago and getting like a C plus. It's like one of the few C's I got in college. I got my ass kicked in there. Just really didn't get it very well. And so my physics is kind of self-taught now. So then I get in a conundrum about this, and I've told you guys this. And then I go talk to Dusty. I'm like, how does this work? And he's stuck too. Like every single time. Every time I'm stuck, so is he. Like this is not easy stuff. So I don't mind like sharing the conundrum of this stuff, because that's what you're really trying to learn in here, is to learn how to think. That's why I didn't get it in college. So I think this is it. I think this is right. Now you might have noticed I just made some space here while we were talking. I want to add something to this. I want to see what you think about this. Isn't the so remember up above, like this was the ball and this was the bat that hit it, and down here this was the ball. Ball has two L's. This was the ball and this is the bat. So the ball had no momentum vertically, but does it have impulse vertically? Isn't that its force? And this its time?
Yeah, because it's going.
Do you think that should get included? I'm not sure. And if it is included, is it positive or negative? Now notice either way, it's pretty negligible. If you take 0.015 times 0.32, you're going to get a teeny number. But theoretically, because we're just trying to learn how to think here, theoretically, does it belong there?
We have the force of the bat, and then we have the force of the ball, and they both have a time that they're.
Yeah, but is that force in the y direction? Because then if we say that, wouldn't we?
Because that force is in the y direction, right? Because the ball's falling. That's the only force. That's the only direction it can have force. So it sort of doesn't belong in the previous one. So does it belong here? And I suppose it is downward. So does that make it negative? I think it does, doesn't it? If it belongs, I'm still not sure it does, but
Is this at contact right now? That's what we're.
well, the left side is like what happened right before contact. What did the ball bring to the bat? And then a billionth of a second goes by and now the ball leaves the bat. And then the other side is what momentum happened after that. So like the equal sign is, a billionth of a second, boom.
So what force would you get on that one? Because technically the Fy and the 0.32 are the two forces, because then you take time out of that and you multiply those or add them up together and give you one single force that yeah, because you take time out because they both have the same time. So it'd be a force of, we don't have force of line.
We can only do that if time is consistent across the.
It
entire-
is for the two times, because the time that's applied on the bat is a 0.015, and that's the same time on the 0.32. So you can take that out, so you have Fy minus 0.32. So then you would add 0.32 to your final answer.
Yeah, which is pretty negligible. So either way, it's close. So even if we're not sure, pretty close. I think it belongs, like if I've got to cast my bet, so to speak, I think it belongs there. And actually the 51.23 number is with it in there.
Oh, 51.23 is with it.
Yeah, because like you said, it's really only adding or subtracting 0.32. It's like it's not making, still around 51 pounds either way.
So it doesn't change anything.
So then if we want to find the final impulse, it's just going to be the square of the sum of the forces.
Yeah, and that's not so much an impulse, it's just a force.
Or just-
So, this is the horizontal and vertical component. I can say, good, I'm done. But if I decided I wanted, I'll do that really quick, but I'll I'll just
What
write
if
it.
we do a fine, free body diagram of the actual contact? And put on, and just map out all the forces that are being done at contact.
So those do belong in that cushion.
I have no idea. Yeah. It makes sense since it's all, because the weight is only applied downwards. Down. It's not applied in the side.
So howsoever, I think it's just kind of cool that we were actually able to use the stuff we studied to turn what was a velocity that we couldn't really control into a force that we could. I just think that's kind of neat algebraically to look at it that way. And so to Thomas's point, if you actually swung the bat, now keep in mind, this is kind of interesting, is you could swing the bat uphill with 139.9 pounds and get this to happen, but you can also swing flat, but the ball just hits the top part of the bat, which makes this very much more confusing too. So I don't have a super good feel about that, but it's kind of cool that we can actually turn velocity into a number of pounds here. Incidentally, when I tried to do this as though impulse and momentum were directionless, I got more like 150 for that answer. So I was hoping to get the same answer so I could go, oh, cool. I've now proven that it doesn't make any difference. This is directionless, but I got a different answer. So now I'm like, oh man. And I couldn't figure out a way to kind of test it, to try to reason out which one is actually true. Of course, what would be really cool would be to go do it and see which one was the actual home run, which was the heart of all ancient scientists trying to, come up with hypotheses, and particularly with respect to the motion of the planets. That's a fascinating one because they would try to predict what was going to happen later, and then they would, go to see if it did, and that would kind of prove the reality of their calculations and so forth. So again, what's that? I know. We can bring 139 pounds of force. For you weightlifters, that's like the bar with 2 plates on it, 245s. It's kind of that much force. You curl that, don't you, Ian? 145 on each side. 135 pounds, just the bar with no collars on it. Okay, we got smarter. We thought more deeply about this equation. We just played with it. We just touched it. We messed around with it. Physics is kind of cool because we can just kind of own every aspect of any kind of motion. Okay, so I think we have just enough time to go look at Gun Guy. That is this class, right? Yes. So, no pun intended. I want to switch over and actually, I put the video on here because I wanted to see it, but I guess I won't because yesterday it seemed like it got all screwed up trying to turn, and this is a PDF file, so I can't just click on that. If it was a Word document, I think I'm able to click on that link, but you can imagine what happens. It's like, and as I said, the bullets just keep coming out. And so he's sitting there still and he goes, and of course the skateboard starts moving and it just picks up speed because he's shooting, if you will, faster and faster and faster. And so all I want to do is kind of play with the equation we played with at the end of the day yesterday, which is really the conservation of momentum equation.
So his acceleration is related to how fast he shoots them.
Yeah, that's exactly right. So he's definitely accelerating in this video.
That makes sense. I don't know what I thought.
So, the main thing should just be kind of like, well, what's going to happen? Could you predict this? And again, did this guy predict that? No, most people are just, go out, jump their bike, see what happens. He's just like, let's just shoot and see what happens. Of course, from probably shooting a gun at some point in your life, there's a certain amount of recoil, but because you're standing on the ground with friction, you don't go anywhere, right? But if you stand on a skateboard, you don't have much friction now. And so all of a sudden you are going to go somewhere. That kind of makes sense, doesn't it? So, you know, I wondered in his case if that took bravery, like that he could have shot and then just flown off on his back, right? And then shot someone or killed himself. Darwin Awards. It looks like he kind of bent over and leaned forward, kind of knowing that he was going to get kicked backwards a little bit. He's kind of hunkered down a little bit, but it really did just start propelling him backwards. So like machine powered skateboard, gun powered skateboard.
They use it on the, like, automatic 12 gauge.
Okay, so I gave you a few basic stuff I just faked up here. Let's say the man plus the gun plus the bullet plus the board. Notice I had to add all that stuff together. If you decided you really cared, it isn't just how much does the guy weigh. Of course, the bullet would feel pretty negligible, right? Relationship to all that other stuff, but whatever, you got to come up with a weight. And then the bullet has a weight and the bullet has a speed. So the interesting thing is, and this is something you can read right off the box, it'll list a muzzle velocity. I think that's the way it's worded. If anybody's more of a gun nut than me, let me know. But you can read right on the package, and that's a reasonable number. Like a 22 or a smaller shell is like 1,400 feet per second. So this is, you know, more of an AR kind of thing. I can't remember if I looked this up, but 2,800 feet per second is pretty realistic. But notice it's not just going to be him, you know, the bullet goes out the same. That's what it does if you stand still. But if he shoots it out there, then the bullet's going to have some speed, but then he's going to have some speed too. Like the bullet's going to leave the gun, but the man's also going to leave the location where the shot was fired, right? So that's kind of an interesting side of this. And so we said yesterday that this is what conservation of momentum looks like. However, I'm going to write this backwards. And actually, I'm going to pull up the note sheet for this just really quick here. Except for the really quick part. There we go. And let's stare at this a second.
We just assuming he's shooting one bullet, just shoot him.
Yeah, that's a good question because he shoots bullet after bullet after bullet, right? So this business of stuff sticking together, because the bullet is stuck to the gun to start with. So in the case of the ballistic pendulum yesterday, we said separate bullet, separate block of wood, shoot the bullet into the wood. Oh, now they're together, right? So they were apart and then they went together. Well, today it's actually the reverse. They were together, then they came apart. So it's the same equation, but I'm going to write it backwards. You see what I mean? So let's see, mass of, why do I keep doing that? Because I'm stupid. Mass of the bullet let's see. I'll just write it out first and we'll stick. Makes more sense over here. Mass of the bullet times the velocity of the bullet when it separates plus the mass of the dude. I'll say guy, gun. Because the only of the four things that caused weight there, the only thing that left was the bullet, right? The skateboard was still there, the dude was still there, the gun was still there. So once they separated, so this is conservation of momentum.
Up on top where we have the weight of everything, is that including the bullet?
Yeah, so the question is what's going on kind of on the other side of this? So it is important to understand that this is before the shot and this is after. And you have some questions that pertain to this, so I'm going to, say a couple things here that you're going to want to understand. But what do we know about what's going on before the shot? So first of all, the two masses are a little confusing. But But really, that's just the mass of everything. Like that's the 180. Does that make sense?
So that's a pound.
That's right. That's the 100 pounds. And so
That's the mass.
that's exactly right. Now, technically, that's not a mass, right? So we'd have to divide by 32.2, but the velocity is actually 0 because the dude shot it standing still. So we really don't even care about those masses, right? What about the other side?
You know, the initial velocity of the bullet or the final velocity of the bullet. And the masses of bullets, once we, well, we know the mass of the bullet, we'll take the overall weight, subtract by the weight of the bullet, and then find the mass for that.
Yeah, so it turns out velocity is a little tougher than you might think. So let's stare at mass first. So mass of the bullet, we knew that, it was 0.2, right? But remember, mass, it's 0.2 pounds. And so we actually have to divide by 32.2. And what does that mean the mass of the guy gun skateboard is then? Because it used to be 180. That's exactly right. He lost 0.2 pounds of his weight, right? So now he's down to 179.8. So the mass is separated here. They didn't come together, they separated. The bullets separated. But the problem is the velocity of the gun, the velocity of the bullet. If you say the velocity of the bullet is 2,800, then the velocity of the gun is actually nothing. The problem with this is you have a frame of motion problem, a frame of reference problem. Did you study that some in physics? You have a bit of a frame of reference. So actually what happens is the speed of the bullet relative to the dude is 2,800, but the dude's moving. So the bullet's moving away from the dude's moving away from the bullet. So he sees it as 2,800, but if you're standing flat on the ground over there and watching, you don't see it at 2,800. The bullet's actually slower than that relative to you who's not moving. Does that make sense? So in other words, it might look something like this. If that's the gun and the bullet goes out this way, this might be 2,700, but the gun would be in motion like negative 100, if you will. And so that would be 2,800 relative to the guy.
Also, we just choose a reference frame.
Yeah, so and we kind of want the reference frame to be the guy, but the problem is the guy's in motion. Does that make sense? So the point is, it's like, how do we write an equation for that? Well, let me just sort of give it to you and then we'll talk about it. So the velocity of the bullet is actually the 2,700. And again, that's with you as the frame of reference on the side. That's how fast it's going relative to the earth. Does that make sense? That's why I'm sticking 27 in here for the velocity of the bullet. The guy was going negative 100. And so the velocity of the bullet with respect to the gun is the 2,800. Do you see why that equation works? Like we could have made that for ourselves, but we have to talk about the velocity of the bullet, the velocity of the gun, and the velocity of the bullet with respect to the gun. That's the issue. So do you see how that's how it plays out then? So my formula is this beauty right here.
So then we know that somebody just plugging the velocity of the guy as well.
So in a sense, what we have is the velocity of the bullet equals the velocity of the gun plus 2,800, because that's the only thing we actually know. Obviously, I made up the 2,700 and the 100 just to kind of make sense of this, right? That's what we know.
Is that velocity of the gun the same one on the one for after? Because on the top one of the.
Yeah, and so that equation right there feeds into the velocity of the bullet and the velocity of the gun up above. That's kind of the idea.
Oh, I thought it was the velocity of the guy.
bullet, yeah, guy, gun, skateboard. Yeah, I'll write that up here. Guy, gun,
Oh, the both, okay.
because that's what's left together, right?
Yeah, okay.
So I just said guy, but I keep saying gun instead.
Almost that
So
same.
what does that actually mean? We actually have two equations, two unknowns now to solve this. Does that make sense? Now, because that bottom one is solved for V of B, does it make sense I could kind of do this without a matrix, or it wouldn't be all that hard to solve? And that's what's kind of cool about this. But let's take the time to do this because I don't really have to cheat this time. Let's just go ahead and just solve this by hand. So I'm going to call this kind of equation 1, and this is equation 2. Maybe I will also highlight this. So if I combine those, then I could say 0.2 divided by 32.2. That is multiplied by V of B, but we said V of B could be replaced with V of G plus 2800. And then that is plus 179.8 over 32.2. And that's multiplied by velocity of G. And so we took two equations, two unknowns, we substituted one in, and now we have one equation, one unknown, and now we can solve for velocity of G. So I didn't really have to cheat to do that, as we've talked about a lot in this class. An engineer might just put both those equations in Desmos just to save time and make sure they don't do something stupid, right? So, in the interest of time, the velocity of the guy gun comes out negative 3.1 feet per second. You asked this question earlier, but I just kind of dodged it. That's after shooting one bullet. Does that make sense? We only had one bullet here. Now he keeps shooting it and therefore goes faster and faster and faster. But that one bullet gave him basically a reverse velocity of 3 feet per second. And if there was no friction, he would just roll that indefinitely. Does that make sense? Skateboards are relatively frictionless, so he'd probably roll a long ways, but you know he would come to a stop because there is some friction. But in a frictionless environment, he got 3 feet per second of that speed. And if I substitute that back into the other equation, the equation 2, then I get 270, 2796.9. So, and this is from your frame of reference. So if you're standing there looking at him, you would say, oh yeah, the bullet's going a hair slower. That kind of feels right, doesn't it? It's going a hair slower than it is relative to him, relative to the earth. And then he got a little speed out of the deal, right? That's kind of cool. Why did he only get a little speed? Well, because the bullet's so light. Does it make sense if he shot that same bullet? It was like a 50-pound bullet and it still shot at that same speed. That's going to knock him backward a lot more. Probably wouldn't have stayed on the skateboard, but interestingly, 0.2 pounds. I mean, that's a really tiny. It's almost like, you know, it's the kind of thing we would ignore in this class, right? Oh yeah, who cares? That's hardly any weight. But that mass actually multiplied by a fairly sizable velocity actually gave him a little bit of momentum, didn't it? So this equation right here, if I remember right, comes up in an assignment question. So you want to think about that. Okay, it can be done. The only thing I want to say is make a note of this. Let me make sure I still assign this and change it because so there's only two questions in 15.3, which is the conservation of momentum stuff that we just talked about. There's only two. 43 is nasty. And so make a note of this in your mind. I'm just going to say this out loud. I have a note sitting in front of me. I didn't do this recently, so I don't remember it off the top of my head. But I have a note here that says, warning, this question involves integrating a velocity equation to turn it into a distance equation. the other reason I say warning is as well as giving you a hint is that means, you know, today's Thursday, that means you might not get that question entirely on your own without some hints. And so that's okay. 43.
Integrating the velocity.
Yeah, you'll have a velocity, you're going to need a velocity equation and you'll have to integrate it to turn it into a distance equation. But fine, get stuck on it and we'll talk about it. Maybe you'll get it. Maybe my hint's good enough. I don't know. Can't remember. So you'll have, I did do this. I'm going to stare at it. Okay, let's get out.